Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into your textbook, starting with sections 1.1 and 1.2. Now, generally speaking, when we have videos here, we're going to be taking a look at basically section by section. I wanted to combine section 1.1 and 1.2 because, to be honest, 1.1 doesn't really have any content in terms of information that we need for the class. 1.1 is really trying to give you guys an introduction into why we take the time to learn and study differential equations. If you look at section 1.1, you'll see that there's a lot of information in there about different applications of differential equations in physics, in population modeling, just all over the place about how important it is to be able to model and understand the rate of change of either a physical property or of a population or in lots of different situations. So 1.1 is really trying to justify why we study differential equations and why they have such a natural relation with modeling. If you want to take a look at 1.1, it's definitely an interesting section, and they set up a lot of sort of famous differential equation models. We'll actually revisit some of those as we move along in some of the later sections that actually deal explicitly with modeling using differential equations, so I'm not going to say too much about section 1.1 right now. Instead, we're going to jump right into section 1.2. And in section 1.2, we're basically going to talk a lot about some basic definitions, terminology, trying to really give ourselves a language to speak and talk about differential equations. So the first thing we should probably say is exactly what is a differential equation. Well, a differential equation is, of course, just an equation that involves derivatives. This separates a differential equation from the standard equations that you guys have been working on your entire mathematical careers, right? The standard equations that you guys have worked on are what we would call algebraic equations, and you know a tremendous amount about solving algebraic equations. You know how to solve algebraic equations that involve polynomials, radicals, logarithms, exponentials, trigonometric equations, all different sorts of functions. You even know how to solve systems of equations. Sometimes you know how to solve or at least understand equations that maybe have many variables in them, all different sorts of things. But what makes a differential equation a differential is that it involves derivatives. And those could be first derivatives, second derivatives, so on and so forth. For some of you guys that are taking more advanced math classes later on in your academic careers, either because you're pursuing sort of a math major or degree, or maybe you're going into a field that has a lot of math in it, you might also see differential equations that are called partial differential equations, where the derivatives in those differential equations are actually partial derivatives. However, for our class, we're going to be focusing on what are often referenced as ordinary differential equations. Ordinary differential equations just is a fancy way of saying these are going to be differential equations that only involve the ordinary derivative. That doesn't mean that we're only talking about differential equations that involve the first derivative. It just means that we're only going to be talking about with a standard derivative, no partial derivatives. This also means that since we won't be using really any partial derivatives in our differential equations, our differential equations will always have only one variable treated as the independent variable. At the beginning of our course, we're pretty much exclusively going to be using x as that independent variable. And remember, if we had more than one independent variable, that's when you would start to use those partial derivatives. But for us, we're always going to have just one independent variable, which means all the derivatives, first order, second order, third derivatives, whatever, are just going to be normal derivatives, no partial derivatives in there. Well, we already sort of mentioned that sometimes differential equations have higher order derivatives in them. You might have a differential equation that involves the second order derivative or the third derivative or something like that. So we have this as our first official definition. Generally speaking, when defining specific terms, I'll try to bold them in the document. I can't always guarantee that that'll happen. Can't also guarantee that we're always defining just a single term. But at the beginning here, because again, we're really trying to flesh out the language and the vocabulary, going to try to make sure we bold these. So, this is the definition of the order of a differential equation. The order of a differential equation is simply the highest order derivative that is present in the differential equation. So this is a very similar concept to like the order of a polynomial, where you simply look for the highest order power in the polynomial. Same idea for a differential equation, you just look for the highest order derivative. So if the highest order derivative is the third derivative, then we call that a third order differential equation. So order, very basic way of classifying different types of differential equations. Now, this next definition here, lengthier one you'll notice, is super, super important. It's because it gives us a very special class of differential equation. So, a differential equation is said to be linear if it can be written in the following form. So this form is that the differential equation can be written as a some function of x times the nth derivative of y plus another function of x times the n minus first derivative of y plus dot 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 times some other function of x times the first derivative of y plus some function of x times y equals a function of x. Now, a couple things before we dissect this definition. First of all, notation. You guys will notice that when you see that like parentheses n, that parentheses n minus 1, that's just a little notation that means the nth derivative or the n minus first derivative. If we wrote something like this, y to the n, then there were no parentheses up there, then we would know that that actually means y to the nth power. But if you see those parentheses up there, that indicates that we're talking about that order derivative. And then, of course, for lower order derivatives, usually like first order, second order, maybe even third order, we would just say like y prime, y double prime, y triple prime. It just gets tedious if you wanted to say the seventh derivative. You don't want to have to write out 7 of those little marks. I don't even know if that was 7. You'd rather just write something like that. So, what does it mean for a differential equation to be linear? Well, this linear format, if you look at it, it basically is saying that the only functions are functions of the independent variable, in this case x. So we have this fn of x, fn minus 1, f1 of x, f0 of x, etc., capital F of x. But notice there are no functions applied to the dependent variable y or any of its derivatives. Said another way, a linear differential equation is basically a differential equation where the coefficients of the dependent variable are only functions of x. So you can sort of see that we're treating these where the coefficients of each derivative or each dependent variable is going to be just a function of the independent variable. Now, not every differential equation is linear. So any differential equation that cannot be put into this format is said to be nonlinear. So we now have two ways of sort of classifying differential equations. We can always talk about their order, and we can classify any differential equation as either linear or nonlinear. One quick note here, not going to be super important just yet, but when we actually start to get into computationally how to solve differential equations, it is somewhat useful. This is one way of understanding linear as a definition. There is sometimes what is referenced as standard form. It's sort of similar to the idea of like putting something with a polynomial with the lead coefficient of 1. It basically says, yep, this form is totally fine, but it's a little bit messy to have this in front. So if we divide through by this function of x, then we can rewrite it into this format. So this is often referenced as the standard form for a linear differential equation. It has the nth derivative of y by itself. Notice then I changed notation and I called these like a1 through an minus 1 through an of x, because of course they're really these original functions divided by fn of x. So not only am I doing a letter change, but they're really different functions. And I also changed this guy to capital G of x because it's really capital F of x over that fn of x or whatever. So there we go. This is what's sometimes referenced as the standard form. Now you will also notice that there's a little bit of subtle re-indexing. One of the things we're going to see a lot in this class is sometimes we're going to have to be talking about things that are like nth order. We don't know how many things are there. So oftentimes we're using indices to keep track of everything. You'll notice that back here, the sort of natural indexing was that if we had the nth derivative, we also had the nth function f, fn of x. But notice here, since I sort of cleared this guy out, I have a slightly different sort of index that I'm using, where these are always sort of combining together to give me n. Again, it's just a re-indexing. It's not particularly important, but just so you're sort of comfortable with different ways to sort of index and understand what you're writing. Here, I'm sort of saying that the index I'm using for each function, along with the order of the derivative, always adds up to n. So you'll know 1 and n minus 1 and 1, n and 0, so on. Just another way of sort of viewing and indexing what we're writing. All right, let's put these definitions sort of to work and take a look at a couple of these examples and see if we can determine if the following differential equations are linear or nonlinear, and then state their order. Even though stating their order is actually the second thing we're asked, let's go ahead and do that first because that should be very easy. So on this first one here, we have the differential equation y double prime minus x squared y triple prime equals sine x plus e to the xy. You should be able to easily see that this guy is going to be third order. Why is this third order? Well, the highest derivative present in this equation is that y triple prime right there, right? So it's the highest order derivative, so this is a third order differential equation. Is it linear or nonlinear? Well, two different ways to do it. If you're pretty comfortable with what I said about linear, you can sort of say, are there any functions being applied to the dependent variable or any of its derivatives? Well, if we look, we can see that each instance of the dependent variable is in its own term. Y double prime, y triple prime, and y are all separate terms, and there are no functions being applied to those. So this guy is, they've got these coefficients in front of them that are functions of x, but no function is being applied to the derivative or the dependent variable. So this guy should be third order and linear. If you're a little less into just sort of saying, can I just deduce that it's linear? Well, if it's linear, you should be able to write it into this format or into this standard form. So let's see if we can shift this around to just fit the basic format. So if I do that, notice I can sort of rewrite it in that descending order here. So I could sort of think about it as minus x squared y triple prime plus y double prime minus e to the xy would be equal to sine x. And then you can sort of see there's the coefficient that is a function of the independent variable in front of the third prime. Technically, there's like a little hidden 1 in front of the y double prime. The y prime term doesn't even show up, but of course we could think about it as 0 y prime. And then we have this minus e to the x as the coefficient in front of the y. And then our big f of x would be that sine of x over there. So this would also confirm that it's linear. Again, for you guys, identifying linear and nonlinear is more important that you can do that identification. You can choose how you feel more comfortable to do so. All right, let's look at B. We've got this differential equation that says cosine x times y prime plus y squared equals x to the fifth plus 1. Very easy to deduce the order. Should be immediately clear that this is first order because the highest order derivative is that y prime. So it's just a first derivative. What about in terms of linear or nonlinear? Well, we can see, let's identify the instances of the dependent variable, the y prime. That's all good. It's in its own term. Got a coefficient of cosine of x in front of it. The y squared, that's going to be the issue right here. This right here, that's a function of the dependent variable, right? It's y squared. It's not the second derivative of y. It's y squared. It's the square function being applied to the dependent variable. That right there is going to make this guy non-linear. Now, I know that this is a little, bad that we're putting it in red, makes it seem like nonlinear is really bad. Nonlinear differential equations are not bad in of themselves. We will study how to solve some nonlinear differential equations, but it turns out that we can develop a much more extensive general theory for linear differential equations than we can for nonlinear. So we do prefer if things are linear differential equations because we can develop a lot more theory about them. But in this case, this would be considered first order and nonlinear, and that nonlinear piece is that. If you want to, on your own, you can try to play around and see if you can write this into this format. You will be unable to because you'll always be stuck with that y squared, which does not fit that form there. All right, finally, we've got this guy, part C here. We've got y double prime times y minus 3xy prime equals 0. In terms of order, should be very clear that this guy is second order. Highest order derivative that's present is that y double prime. If we look at this term here, that minus 3xy prime, that's all good for being linear. You've got a coefficient, that minus 3x, that's a function of the independent variable, and then with that y prime. But this right here is going to be a problem. This y double prime y, not going to be good. Why is that? Well, in this definition of linearity, right, all the derivatives and the dependent variable are always in separate terms. And here they are mixed together as a product. You might say, well, why can't we divide? Well, if you try to divide by that y, what's going to happen is then you're going to have y prime over y in this term. So you'd have y prime over y. And then again, the derivative of the dependent variable and the dependent variable would be mixed together. It's always going to be nonlinear here. So this guy is also nonlinear. So again, as soon as you find one component that is nonlinear, the entire thing is going to be nonlinear. And once again, if you want to, you can mess around and try to put it in this format, and it'll never work there. So there we go. There's just a couple quick examples of determining if something is linear or nonlinear and talking about the order of those differential equations. All right, let's move on a little bit more and actually talk about what it means to solve a differential equation. Now, it's a little bit interesting in this beginning of this class here because it actually takes us several sections before we're ready to start solving a differential equation. The first time we'll actually learn a method for solving differential equations is actually in section 1.4. Right now, we're just building up a lot of language and sort of some theory behind what it really even means to solve a differential equation. So we're not quite solving them yet. We're just talking about what it would mean to be a solution. So let's go ahead and talk about this definition here. So a function y equals f of x technically doesn't even need to be a function. It can be like a relation or something like that, as we'll see in these examples. But we'll start with our definition of saying a function. It's got to be at least n times differentiable. Why is that? Well, if it's going to be an nth order differential equation, then it's going to involve the nth derivative. So you better make sure that you can actually differentiate your function n times. We call it a solution to an nth order differential equation on some interval I if, when you substitute y prime, all the way down to the nth derivative of y into the equation becomes an identity that is true for all x in I. Now you'll notice this little E symbol there like that. That means as an element of, or you can just read it as in. So you can just read that as x in I. So what is important here? Well, it basically means that something is considered a solution to a differential equation if when you plug it in for y, the derivative, the nth derivative, so on, what you have is you have an equation that becomes an identity. And remember, an identity doesn't mean that it's sometimes true. It means that it's always true. So in other words, when we're talking about solutions here, we're talking about functional solutions. They don't plug in and give us like one answer. They plug in and they make it always true for all the x in the interval we're working on. So this definition, it should be pretty clear, but I want to just jump right in to a couple examples of checking whether or not given functions are solutions to corresponding differential equations. Now again, notice that we're going to be doing this. Some of these are actually pretty complicated, yet we don't even know how to solve differential equations yet. And that's because right now, we're just checking if things are solutions. We're not actually solving them. We're just being asked, hey, here's a potential solution. Does it actually work? So let's see how to do that. So for part A, we want to know, is the function y equals e to the 2x a solution to y prime squared minus 3y equals e to the 3x? So we want to know, is y equals e to the 2x a solution to y prime squared minus 3y equals e to the 3x? Quick little note here off to the side. You guys should be able to clearly see that this is first order because it only has that first derivative in it, and this guy is also non-linear. Why is it non-linear? Because we have y prime squared. We have a function being applied to the derivative of the dependent variable, so this guy is non-linear. All right, what's the best way to actually check this? Well, we're going to use like what is called a left-hand side, right-hand side approach. So we're basically going to plug this into the left-hand side, plug it into the right-hand side, and see if the two sides are equivalent. To do that, though, it's probably nice ahead of time since we're going to need the first derivative to figure out that first derivative. So let's go ahead and do that. So we have y equals e to the 2x, and that means y prime is going to be 2e to the 2x. So let's go ahead and check what happens on the left-hand side and the right-hand side. So for the left-hand side, we have y prime squared minus 3y. So according to this, that means that y prime should be replaced with this, and the y should be replaced with that. So that means we should have 2e to the 2x squared minus 3 times e to the 2x. And I suppose if we simplify that a little bit, it looks like we'd get 4e to the 4x minus 3e to the 2x. On the right-hand side, could potentially have, things that involve y or y prime or whatever, but in this case, it just involves that e to the 3x. So the right-hand side, we just immediately know is e to the 3x. Now, is the left-hand side and the right-hand side equal? Well, you could maybe think of some x values where they might be equal. You could maybe realize, oh, hey, at x equals 0, this is like, 4 minus 3, which is 1, and over here is 1. But that's not what an identity means. An identity doesn't mean that sometimes the left-hand side equals the right-hand side. An identity means that the left-hand side always equals the right-hand side. And it is very clear that the left-hand side doesn't always equal the right-hand side. So left-hand side does not equal the right-hand side for all x, right? Definitely not true for all x. We could maybe find some x where it is true, but it's not always true. So what this tells us, so y equals e to the 2x is not a solution to the differential equation. So there we go. That guy is not a solution to the differential equation. We don't know what is a solution to the differential equation because we haven't really learned any techniques for solving differential equations yet, but we know that that guy that was given to us, y equals e to the 2x, does not work. All right, let's give ourselves a little bit more space. We'll move on to another page and take a look at B here. So for B, we want to know, is this a solution to this differential equation on this interval? Now, a lot of times in this class, our interval, like in A and also implicitly in B or in C, is just all real numbers because no interval is given. But sometimes you'll see something as an actual interval that is stated. If an interval isn't stated, it's assumed to be all real numbers. But in this case, we're only working on 0 to infinity, which makes sense because notice that like the solution that's being mentioned, c times square root of x, only makes sense on 0 to infinity because of some domain issues. So sometimes you guys will see that. Most of the time we're just working with all real numbers or the interval that works best, but sometimes you'll see it explicitly given. What's interesting about B here is that it's saying that it's actually an unknown constant in front of it. So we're actually saying that this entire family is a solution to this, which we'll see actually is a very important concept overall. So let's see if it's actually true here. So for B, we want to know, is y equals c root x a solution to xy prime minus 1/2 y equals 0? Quick note here, this one is first order. That's for sure. It's only got a y prime there, and the y prime and y are separate terms, no functions of either. So this one is first order and linear this time. All right, let's actually check if this thing is a solution. So y equals cx to the 1/2. And I guess that would tell us that y prime then would be 1/2 cx to the negative 1/2. Let's try our same approach. Let's do a left-hand side. Left-hand side is initially xy prime minus 1/2 y, which we could replace as x 1/2 cx to the negative 1/2, and then minus 1/2 cx to the 1/2, just by replacing that xy prime there, replacing the y prime with what we found for y prime, and for y, what we were given for y. We can do a little bit of simplification. That's 1/2 cx to the 1/2 minus 1/2 cx to the 1/2, and that simplifies to 0. What do we have on the right-hand side? Well, the right-hand side is always 0, so we get 0. So this is an identity. It doesn't matter what x is. The left-hand side is always 0. Right-hand side is always 0. So the left-hand side equals the right-hand side for all x, technically in 0 to infinity, because that's what we were asking for. So that tells us, so y equals c root x is a solution. So that means this entire family of functions, y equals c times root x, it doesn't matter if we do 2 root x, 10 root x, pi root x, negative 16 root x, all of those will be solutions to this differential equation. Again, we don't quite know yet how to arrive at that, but if we are given something and we just want to check whether or not it's a solution, we just plug it in and see if it gives us an identity. All right, last one's going to be a little bit messy, but it'll give us a chance to sort of review some implicit differentiation stuff. So let's go ahead and take a look at that. So we'll give ourselves one more page on that. So we want to know, is this relation, not a function this time because it's implicitly related x and y, but we want to know, is that a solution to this crazy differential equation? So for C here, we want to know, is x cubed y squared minus e to the xy equals 1 a solution to 3x squared y squared plus 2x cubed y prime equal to x e to the xy y prime plus y e to the xy. All right, so we want to know, is this a solution? So what we're going to need to do is we're going to need to determine something about y prime based on this and then plug it in. Now, of course, to determine y prime here, we don't want to try to solve for y and do it explicitly. We want to try to do it implicitly. So we have x cubed y squared minus e to the xy equals 1. Let's go ahead and differentiate both sides of that. If we do that, we should get something like 3x squared y squared plus 2x cubed y prime That's using implicit differentiation and product rule here. And my bad, this y floated down a little bit. He should be up here. Okay. And then we'll do the same thing here. We'll have to do a little bit of a sort of product rule up top. So when we differentiate with respect to x, we should get minus y e x y. And then when we handle differentiating the y there, we should get minus x e x y y prime. And that's going to equal 0 there. A little bit messy there because we had to use a product rule here. And then here, we're getting that, you know what, maybe this is correct, but maybe it's a little bit clearer to you guys if we get minus exy, and then in part of chain rule, we differentiate in here, and we get y plus xy prime. That's probably more the standard way that you guys would have seen how to get that. So there we go. Same expression, but a little bit clearer there. All right. What can we say with this? I suppose we could try to solve for y prime there. So it looks like we get like 3x squared y squared plus 2x cubed y prime minus 3xy minus e to the xy prime. And then we could gather some of this stuff onto the other side. So this tells us that 2x cubed y prime minus e to the xy prime is equal to e to the xy minus 3x squared y squared. And then delightfully, we could get that y prime is e to the xy minus 3x squared y squared over 2x cubed y minus, and I'll put the x in front now, x e to the xy. And you know what? I will do the same back here. I think I prefer it in front there. That's a little more standard looking. All right, there we go. Does that confirm anything? Not really. That just gets us what the derivative looks like. But now we can actually plug that in and take a look at whether or not that makes that an identity. So let's go ahead and do our left-hand side, right-hand side approach. So our left-hand side is 3x squared y squared plus 2x cubed y prime. So if we plug in this y prime, it's going to be pretty messy looking, but we can just pop that in there. So this is 3x squared y squared plus 2x cubed y times y e x y minus 3x squared y squared over 2x cubed y minus x e x y. We can also go ahead and take a gander at the right-hand side, which is going to be pretty messy as well, but we can take a look. X e x y, y prime plus y e x y. If we pop in that y prime, we get x e x y times that y prime, which is y e x y, minus 3x squared y squared over 2x cubed y minus x e x y plus y e x y. Okay. Now we have to wonder to ourselves, are these things actually equivalent? Well, it's probably going to take a little bit of doing because we probably need to go ahead and make some common denominators and actually see what these expressions look like. So let's go ahead and do that. A little bit messy, but fun to sort of work through all that stuff. So let's just copy that, and we'll give ourselves one more sort of page here. All right, there we go. So we can do a little bit of multiplying out here, and looks like over here, if we multiply this thing on here, we can continue on and call this 3x squared y squared plus what, 2x cubed y squared e to the xy minus 6x to the 5th y cubed over that 2x cubed y minus x e to the xy. And then I suppose we can multiply this by this here. So that gives us what, a 6x to the 5th y cubed minus 3x cubed y squared e to the xy plus 2x cubed y squared e to the xy minus 6x to the 5th y cubed all over that denominator, 2x cubed y minus x e to the xy. Delightful, but we've got a nice cancellation there, so we've got that stuff out. So we've got minus 3x cubed y squared e to the xy plus 2x cubed y squared e to the xy over that denominator 2x cubed y minus x e to the y. All right, we could mess around, maybe find some other simplifications here, but let's try the same trick over here and just see if we get something that looks equivalent. So let's multiply that stuff out. Looks like we should get x y e x y squared there, minus 3x squared y squared, minus x cubed y squared e x y over 2x cubed y minus x e x y plus y e x y. Then we'll multiply this onto here so that we can actually make that common denominator and combine. So it looks like we get xy exy squared minus 3x cubed y squared exy plus what? 2x cubed y squared exy minus xy exy squared over 2x cubed y minus x e x y. Oh, got a nice cancellation again. This guy and this guy. Minus 3x cubed y squared e x y plus 2x cubed y squared e x y over that 2x cubed y minus x e x y. And what do we know? This side, they're true, not just for some random x's and y's, but for all x and y. So our left-hand side equals our right-hand side for all x, y. So this is a solution. Now, this is absolutely horrendous, right? There was just a lot of implicit differentiation, a lot of algebraic manipulation that had to go on here. Let's go back and just take a moment to see if there was a more clever way. I wanted to do this mainly just to show you guys that implicit differentiation is always going to be pretty messy here. But let's just take a quick look back at where we sort of left off here. Let's think about right when we got to here. Back here, which is where we sort of took the thing that we potentially thought was our solution, we differentiated it, and then we got right to here. We could have tried, if we wanted to, messing around a little bit with this, maybe bringing this over here, and then sort of looking at the result of that, and just seeing if we got an expression that matched the differential equation we claimed. Actually, if you guys want on your own, you can try bringing this over here, distributing y prime back to where we actually had it here, and actually just manipulating this expression right here by bringing this guy over here, and we just immediately see, oh, hey, that's the differential equation. We're all done. But that's pretty lucky that you would catch that and you would just get away with it in that sort of one line. So it's a better idea is, I guess, a loose term here. It's a more general idea to sort of use this left-hand side, right-hand side approach. But do be aware that with the left-hand side, right-hand side approach, it can get very messy since we're working through that stuff. That's going to do it for this video. Now we understand what it means to be a solution to a differential equation. In the next video, we're going to be talking a little bit about what it means to be an initial value problem for a given differential equation.